Let's see if I can see this here. Yeah. All right. So we left off last week talking about bases, right? So we'll pick up on that. We'll do another example and a couple examples, or we think about different ways, and then we'll kind of transition to the next thing, which is we're going to be talking about continuous random variables. Could do some binomial and Poisson stuff on Wednesday and Friday. Monday, we should be doing continuous distribution. Wednesday next week, I should be doing an exam review in class. Right? I might also get some additional kind of videos of me working through some of the problems that we won't have time to work through in class up on that YouTube page. And then next Friday will be that first exam. So I thought tentatively I might have to reschedule it. As of right now, we should be kind of okay and on pace. If something does happen to where I won't be able to be here that Friday, you may have a proctor instead of me for the exam, but I think right now I should be here. So just to kind of point some things out. So you've got that Connect and Excel assignment that are up there you can start working on. What am I looking for? Here we go. Practice materials. I've got up to 2 different practice exams. I have just like a regular answer key that lets you know what kind of it's all, the majority of them are all multiple choice, so it tells what the answer is. But then I'm going to have words, I call them detailed answers, right? Or answer key detailed, where I kind of have it typed out, like what formula you use and plugging the numbers in and kind of showing a little bit more of the steps that you would need to get to that correct answer. Okay. Any questions on anything before we kind of jump into the material here? Just making sure everyone's aware of that kind of practice exam folder. And if there's no questions, we will get started. Okay. So we worked through kind of an example last class. We're talking about these setups where we have 2 states of nature. We don't know what state we're in. We then run some experiment or have some tests. We see the outcome of that test. And from that outcome, we can then update the probability, right? Find a conditional probability, okay, of what the true state of nature is. So one thing that I don't think we went over are these, because we didn't need it for last class, but we'll need it moving forward, is a couple of traits, right? So this one we kind of talked about. We said the 2 states of nature, we kind of think about it as we're either in one of those states or the other. So kind of think about these would be mutually exclusive events. There's no overlap. Can't have the disease and not have the disease, right? So instead, we're writing these as a complement. We're just thinking about these will be, so we know the probability of an event and the probability of its complement add up to 1. So for us, those 2 states of nature, those probabilities should add up to 1 as well. Okay, it's the same kind of idea as that complement rule. The one that maybe isn't a little as intuitive, I tried to allude to this a little bit when we were looking at contingency tables, but let's think here, and I'll put some words to this. So let's think about, use the HIV example again that we had from last class. So given, so what this second thing is really saying is that, hold on. Being positive here, right? That if I condition on the same state of nature, right? So here I'm conditioning on the same state of nature, whether that's the first or second. And this one I chose being HIV positive as a state of nature. So given that I know, like it's like I pulled someone out of a huge group, and then I'm interested in what's the probability they get a positive test result on this HIV test. Well, if you then tell me, given that person, I'm telling you they have HIV, I now know that the probability that they get a negative test result, I think it was something like 0.001. The only other outcome they can have, we said for now, we're saying there's no inconclusive experiments or no inconclusive tests. So given that they have HIV, if the probability they get a negative test result is 0.001, what does the probability they get a positive test result have to be? They're the only 2 possible outcomes. This one person is either going to get a negative test result or positive test results. So those probabilities should add up to 1, right? So you can kind of think about here, this would be 0.999. You could work in either direction, right? So whenever we condition on the same state of nature, so if we've got the same thing on the right-hand side of that vertical line, that conditional, that given line, then the two different outcomes of the test, E and D complement, here getting a positive, negative test result, well, those are the only two possible outcomes to see on that test, so they have to add up to 1. Now, if I condition on something like this, like different states of nature, and then I try to add up the probability of seeing certain outcomes on the test, all bets are off. I have no idea what those probabilities are going to add up to. In fact, they could add up to being over 1, depending on the situation, right? Because it's conditioning on the same state of nature. It's almost like I've now limited my space to this one area. So if I condition on different spaces, well, on one of them, I'm looking at this area, but maybe on the other, I'm looking at a much bigger area. So there's no telling what those probabilities add up to. But if I'm just looking, like, let's say we had something like this, try to draw an easy one. So let's say this is your two outcomes of the test. Kind of splits the experimental outcome space in half. I then have, we'll call this state of nature 1, right? So I condition on that state of nature. It's almost like I've gotten rid of all these different experimental outcomes out here, right? I'm only left looking at this circle. So maybe the remaining space, instead of 1, maybe it's something like 0.5, right? Well, even though this area would be 0.25, this area would be 0.25, if I exactly have this split in half just to make it a little bit easier to think about. Well, 0.25 of the remaining 0.5 area, well, that's just a probability of 0.5. And then 0.25 of the remaining 0.5 area, that would be 0.5 as well. Those should add up to 1. Right? It doesn't have to be 0.5 and 0.5. You can kind of use different numbers and prove this to yourself. Like, let's say instead, oh, I'm gonna make this easy on myself. Let's say I did 0.2 and 0.3, right? Well, now, given that I'm in this state of nature, what's the probability I see this outcome of the test, E? Well, it's 0.2 out of 0.5. We're really just finding a conditional probability there. So the probability that we see E, this outcome of the test, be 0.4, which would mean the probability that given we're in this same circle, how would we see the other outcome of the test? 0.3 over 0.5, sure enough, ends up being what would get us up to 1. I guess you can, if you want to, start plugging in numbers that up to 0.5 to prove this to yourself. But this is kind of the general idea of what we're doing. And when we condition on the same state of nature, the probability the two outcomes of the test have to add up to 1. Okay. I don't think I have something up here, but there's something else that we could maybe figure out from this too. So that'll, for Bayes' theorem, that'll be about all we need. But there's another thing very similar to this that will allow us to maybe make certain things a little bit easier, make our life a little bit easier. So here we had E complement, and then we conditioned on that first state of nature. Right? So what if instead of conditioning on the state of nature, I conditioned on that test comes back positive? So I'm going to think about two different probabilities here. The first is, given that test comes back positive, what's the probability the person is HIV negative? And then the other is, given that we see a positive test result, what's the probability they actually have the disease? Okay. Well, similarly, once I condition on the same thing, I'm now left only with the people who see kind of a positive test result. Well, the people that get a positive test result then either have the disease or they don't, right? So when I'm conditioning on the same outcome of the test, okay, we're calling that E, if I add up the probability of being in the two different states of nature, because they're complements, right? It's basically like the same drawing I had before. You're just now in the space of not S1, you're in the space of just people who got a positive test result. Of that remaining space, a fraction of it is people who actually have the disease, and a fraction of it is people who actually don't. Now these, when we condition on this, the outcome of the test, this is what we're actually using Bayes' formula to compute, right? Given that I see a positive test result, what's the probability the person actually had HIV, right? So kind of just a reminder of how we did that, and I'll work through another example. We had all this information given to us. Back to that in a second. We wrote down what we were given. Right. We then wrote down what we were looking for, right? To probably see a positive test result, probably actually have disease. We then write out Bayes' formula in the context of our example. We'll go back to that general form here in a second. I've got to kind of write it out for us. And then it's just a matter of plugging in our probabilities. Okay, so once we plug everything in, we had that was about 0.3. That's kind of where we left off. Yeah.
In this scenario, all the things are mutually exclusive, is that right?
The two outcomes of the test are mutually exclusive, and the two states of nature will be mutually exclusive.
So does Bayes theory only work with things that are mutually exclusive?
For our sake, yes. You can complicate it to where you could factor in that there's intersections, and so then when you're rewriting some of these things, it's not really called based, but there's a way you could do that if you had some overlap in your states of nature. Yeah, but for actual using Bayes' theorem, now you could add more states of nature. Like you could do the same thing, but like with 4 different outcomes of the test and 4 different states of nature. Maybe like you're doing something like blood type. You could actually use Bayes' theorem to, like, given that they have certain markers, what's the probability their blood type is this, and you've got just more possible. You can't have O positive and AB negative blood at the same time, right? So but I won't do anything like that for you guys. I'll keep it 2 states of nature, 2 outcomes of the test, and they'll both be mutually exclusive. Yep. What else I want to say here? So this is kind of where we left off. But I'll go back here and show you another way, and I'll work through an example, and I'll draw the tree for that example. But one thing that sometimes can help make this a little bit easier is drawing out what we call the probability tree. Now, it kind of just depends on how your brain works. Like if you see these equations and it makes more sense, okay, I'm conditioning on the same thing, 2 different states of nature, like these should add up to 1. But if you draw down the tree, maybe it can help you remind you that a little bit easier. So notice the very first kind of ring, or whatever, is my 2 states of nature, right? Either being HIV positive or HIV negative. Then if I go down the HIV negative branch, this state of nature, I'm only going to condition on that state of nature, right? So here I looked at the conditional probability of getting a positive test result given the person's HIV negative, and I also have the probability of a negative test result given the person's HIV negative. So on this branch, I conditioned on the same thing, 2 different outcomes of the test, these should add up to 1. Sure enough, 0.99, 0.01, add up to 1. And then on the other side, right, the other state of nature branch, right, I've got conditioned on that state of nature, the probability for 2 outcomes of the test, or the conditional probabilities, these should add up to 1 as well. So the 2 states of nature probability should add up to 1, and then conditioning on the same state of nature, the 2 outcomes of the test should add up to 1 on each side, right, on each branch. That doesn't help you at all, then don't worry about writing on a probability tree, but for some people, this kind of makes it a little bit easier. Okay. So let's go through. Before we start the next example, I want to make one point, which I forgot when I was doing this. So we left off here last class. So what we had was, given that there's a positive test result, the probability of the person that's HIV positive is 0.38. So given that I see someone have a positive test result, then what would be the probability that they don't have HIV? Well, if there's a 38% chance they do, yeah, just whatever get me up to 1 or whatever would get me up to 100%. If I want to talk about it in percentages, or 0.62. Okay. Conditioning on the same outcome of the test, and the probability of being in either state of nature have to add up to 1. Okay. All right, so let's go through another example. It might seem a little bit goofy at first, but I think I can turn it into a relevant example. So do we have everything written down up here? Anybody need me to keep this up? All right. Also, black markers kind of don't make things a little bit exciting. So here I'm kind of giving some information, and then we'll kind of work out, given that information, do some other stuff. So the probability, well, I'll just show everything. I'll talk about it first, and then I'll draw it up the tree. So we've got 2 conditional probabilities we're told. So there's some truth theorem the government comes up with, and they're going to use it to, make sure that they're correctly capturing everybody who's either innocent or guilty, or letting everyone who's innocent go. So the only problem is it's in the early stages, and right, given that it makes somebody confess, or sorry, given that someone is innocent, the probability it makes them confess, right? The truth serum makes them say they're guilty will be about 0.01. So it's got like a false positive rate of 1%. Given that someone's guilty, the truth serum doesn't work about 10% of the time, right? So given that they're guilty, 10% of the time, they still claim their innocence, right? Usually the truth serum, if it's working right, should make them confess to what their actual state of nature is. So we then have this idea that the probability that if we were just to select somebody at random, brought into questioning or whatever, that 5% of suspects are guilty, right? So relatively low. So what we've got there is the probability of being guilty without any additional information is 0.05. So if I'm doing like a little probability tree here, and I don't have to do it as a tree, but I can kind of think about if this is all I'm told, well, what's the probability of the other state of nature? Might be something I need. Yeah, right. The probability that someone is innocent, well, we're going to assume here you either committed the crime or you didn't, right? There's mutually exclusive events. These should add up to 1. Okay. From there, and we don't always have to do this. I'll kind of write out Bayes' theorem and show you that like some of what I'm about to do would have been overkill. But if we do it this way, we'll always have all the information we need, no matter what probability we're asked for. So here I'm looking at the branch of the guilty or the guilty branch of the tree. Okay. So I'm going to condition on that state of nature that the person actually is guilty, right? I'm probably going to run out of room here, but so if I'm conditioning on the same state of nature, and I then want to know, okay, what's the probability the truth serum makes them say they're guilty? Probability the truth serum makes them say they're innocent. Okay. Well, I'm told one of those, right? So given that they're guilty, the probability the truth serum makes them say they're innocent is what? 0.1. So given that they're guilty, what's the probability the truth serum makes them say they're guilty? Yeah, these two things should just add up to 1. Right? We're on the same branch, we've conditioned on the same state of nature. Any questions on that before I keep going here? It's making sense so far. I might run out of room here, so I'll write a little bit smaller. So if you can't read something, let me know. So now we're going to think about conditioning on the other state of nature, right? We're on the other branch over here. Well, now the truth serum can either make this person say they're innocent or that they're guilty. Which of these do we know? Well, given that someone's innocent, the probability they incorrectly confessed to the crime was told to us to be 0.01. So given that they're innocent, the truth serum actually doesn't make them confess or actually works correctly. What probability? Yeah, these two things should add up to 1. So if it helps to do the tree, you'll always have all the information you need. And we'll kind of see as we work through this one why that makes it a little bit easier. So I don't know if I have the general form of the equation. Let's see. So we got down all the probabilities. Oh, I guess I should start out with what are we looking for, right? So I wrote down what we were given, but what do we actually want to find? So if the truth serum indicates guilty, what's the probability the person's actually innocent? So what we're saying there is, given, right, the thing that we know is that the truth serum made the person say they're guilty, and we're interested in what's the probability that they're actually innocent. Now, when you think about this truth serum now is going to be our outcome of the test, and the state of nature we're interested in is, are they actually innocent, right? Is that the true state of nature? So what we can do is write that Bayes formula out in the context of our example. So just to kind of remind you, so we'll do probability. I'll write this out and then I'll kind of use the board to make this point. I'll get out of the way in just a second. Oh, sorry. I was looking at this and I'm just going to write out in the general context. This is E. This is E. And then probability of S2 times the probability of S2 given E. Okay. So this was like the general form of that Bayes theorem. All I did up here was write it out in the context of my example. My state of nature I'm interested in is the person innocent? So everywhere where there was an S1, I plug in the word innocent, or I, so abbreviate it here. The outcome of the test that I'm interested in is the truth serum making them say they're guilty. So everywhere where I had an E, I'm writing that in. And then the only other thing that I would have to find is, well, what's the probability of that second state of nature? Well, if the probability of that first state, the probability they're guilty was what, 0.05? We said using the tree, it was pretty easy to see. The probability they're innocent or the other state of nature is 0.95. Okay? So at this point, we've got all the probabilities we would need. Right? So the probability they're innocent, 0.95, probability they're guilty, 0.05. Given that they're innocent, the truth serum made them say they're guilty. We had that probability told us to be 0.01, 0.01, 0.01. And then given that they're guilty, what's the probability the truth serum made them say they're guilty? Well, we weren't directly given that, right? So if we plug everything in, we're like, oh, I'm missing something. But if we had done the tree ahead of time, right? I was told this, that given they're guilty, the truth serum doesn't work 10% of the time, right? Or the probability they remain kind of saying they're innocent is 0.1. But from that, I could then determine, okay, then given that they're guilty, the probability the truth serum actually works would be whatever gets me up to 1, right? So 0.9, okay? So, well, my graphic's a little off there, but right, it should be kind of substituting that in for that conditional probability. We already kind of talked about that and found that using that probability tree, okay? Any questions on this? Okay with this so far? Okay, so I don't know what this ends up being 0.174. Okay, so it's kind of interesting. One thing I like to do is try to break down Bayes theorem. So we've got the numbers up there, but let's think about what they represent. So it's anytime we have probabilities, we really can talk or think about them in terms of frequencies. Because it represents the number of people out of all the suspects, right? So these individuals were everyone who was innocent, right? The probability they were innocent, so we know they're innocent, we're conditioned on they're innocent, but confessed to the crime. Well, even though this truth serum has a pretty low false positive rate, right? It doesn't incorrectly work that often for innocent people. Most people are innocent. Most people haven't committed a crime. So if you start bringing people in and giving them the truth serum and asking if they commit all these different crimes, well, the majority, 95, where is it, over there, 95% of people haven't committed a crime. So it's a large number of people. So even 1% of a really large number is going to represent a pretty decent group of individuals, right? You think about administering this truth serum to every person in the US, you know, we have what, 95%. So I'm talking about there, 275 million, and then 1% of that. So you're talking about 2.75 million people. While there's only 5% of people who are guilty. So this second group in my denominator represents everybody who's guilty, and the truth serum made them confess accurately to the crime, right? So it's like, I only have two types of people who confess to the crime. People who are actually innocent and people who are actually guilty. So that's kind of like my total number of people who are going to be saying that they're guilty or confessing to the crime. Problem is there's not that many people who are actually guilty of these crimes, just 5%. So maybe 25 million people in the US, and we gave it to every single person, but we know that, oh, where is it? The truth serum makes them say they're guilty. It's going to capture 90% of that. So 90% of 25 million, you're talking roughly 22 million people there. So, you know, we have a pretty sizable group of individuals who are guilty and confessed. We also have a very sizable and actually a larger group of individuals who would be innocent and then confessing the crime, which is why once we actually say, okay, given that the truth serum made them say they're guilty, what's the probability they're actually innocent? Well, it's pretty far away from 0, right? And this really will kind of play out as long as we have kind of any type of false positive or false negative rates, right? And anytime we have this huge mismatch in the probability of the two states of nature. Okay. All right. Any questions on this? You're kind of okay with how I set that up. So I'll give you guys a little, I actually think I actually have to go back here. Oops. not back there. I wanted to exit out of this. So I thought I had this started up, but apparently I didn't. So I want to give you guys a little bit of time to work on this next question. And then we'll kind of talk about it. So, given everything that we've talked about, we just solved for the probability that given the truth serum made them say they're guilty, the probability they were actually innocent was 0.174. Okay? So if instead we have exactly the same setup, but instead now, so remember here's the general form of our Bayes theorem problem. Now I want to say, given that the truth serum indicates guilty, what's the probability that they're actually guilty? So my state of nature that I'm now interested in is whether or not they're guilty, not whether or not they're innocent. So I'll give you guys a little bit of time, talk to the people around you, a couple minutes here. Try to kind of use Bayes theorem or use some of the other stuff that we've talked about. This might be easier to solve than you would think, given what we just did. But here is what we're looking for, right? Given the truth serum made them say they're guilty, what's the probability that they're actually guilty? Okay. Like I said, you guys don't have to be quiet. All right.
What is the bottom of the parentheses on this? What is the
S2 given E. Go for about another 20 seconds here and we'll talk about it. All right. If you haven't gotten an answer in, take your best guess here. I got 13 of us, so 13 here, 4. All right, 14. All right, close it out. So there's two ways of doing this. All right. Show you the hard way first. Okay. So I kind of wrote this out so that you know what you're looking for. So you could write this out in the context of your example. So for us, the probability of S1 would be the probability they're guilty. S1 given E would be, well, given, I had this backwards for you guys. For the general form, my bad. I'll give everybody credit for this one. It should be the probability of the outcome of the test that you're interested in, given these different states of nature, right? So here we go, kind of conditioned on that the person's actually guilty. What's the probability the truth serum makes them say they're guilty? Now, one thing you can kind of notice, this first component of the numerator is always, of the denominator is always the same as the numerator. Right? So I'm just gonna use that. You could write that in there again, but just to save some space, this is always gonna be the exact same thing. Right? And then the second thing was, well, what's the probability of the second state of nature that they're innocent times the probability that given they're innocent, what's the probability they actually confess guilty? Right? And then you can go ahead and plug your probabilities in. But the easier way to do this would be to do what? Did anybody? Exactly, right? Because if I know the probability that given truth serum makes them say they're guilty, the probability they're actually innocent. Well, we said if we condition on the same outcome of the test, the two different states of nature, those conditional probabilities should add up to 1. So I think before we had found was 0.174, right? So that would make the probability of what we're looking for now, just whatever gets us up to 1 or 0.826. Okay.
Can you solve it with like plugging in the numbers in the base?
So we could do what? Probability of S1, so probably they were guilty was 0.05 times the probability given that they're guilty, the true serum makes them say they're guilty. I have to go back because I forget what all these are. I think it was 0.9. And then once again, that first part of the denominator is always the same as the numerator, so that makes it really kind of easy there. And then the probability they're innocent, 0.95 times given that they're innocent, the true serum made them only say they're guilty 1% of the time. So you'd have something like this.
I did that and I spoke it out and I could have done just a calculation, but I got like 0.3 something.
Let's see. Mess my numbers up.
Given I could have just typed it in my calculator wrong.
My guess would be what happens in these base theorem problems is if you're not careful with your order of operations, it can really screw it up. So let's see if we had what 0.05 times 0.9 divided by 0.05 times 0.9 plus 0.95 times 0.01. Oh, which is why it's probably a little bit off. So I should get about 0.833. I look at this wrong. 0.9, 0.955. Oh, this was what? 0.95, not 0.591. There we go. So my guess is you probably didn't have parentheses here, kind of what's in the denominator.
I did them all separately. That's weird.
I don't know.
I got the numbers, I didn't mess up my time.
Okay. Yeah, so I mean, you can break this down in a step, and that does kind of help with that a lot of the time. Calculating these numbers separately. Yeah, but when you're entering in, make sure then if you're breaking it down in steps, I would calculate this number, calculate this number, calculate this number, but then calculate what this is. That way you only have one number to divide by another number. Because even if you do these separately, you could still kind of screw up your order of operations there in the denominator. All right. And I checked that, not to be a jerk. I checked that because I make mistakes. So it's very, very possible when you tell me these things that I could have made a mistake. So I want to double check that I did not. But kind of here's, oops. So we kind of solved this one. I don't think I have the answer pop up here, but that would be that 0.826. Okay. Any other questions before we keep moving here? So I want to give some context why I chose to do this. What seems like stupid truth serum example. But think about it, like a truth serum is really just a jury, right? So the truth serum was trying to get at what the underlying state of nature was the person innocent or was the person guilty? What's the same thing a jury is trying to do, right? And so you could basically, everywhere we have truth serum here, you could just replace that with the word jury, right? And then we start to think about some interesting things, right? So now we're saying, given that someone's guilty, what's the probability that the jury finds them innocent, right? Given this underlying state of nature, what's the probability that we see this certain outcome of the test? Right? Now, we generally don't like that, letting innocent people go free. You also have, given that someone's innocent, what's the probability the jury finds them guilty, right? So this would be people who are incorrectly convicted. We could find these, we wrote this down kind of with Bayes' theorem. Let's say I wanted to find the probability that given the jury found someone guilty, what's the probability they're actually innocent, right? So given some outcome of the test, what's the probability of some underlying state of nature? And this would be like, you know, if I'm looking at someone who's in jail, who the jury found guilty, what's the probability they actually shouldn't be there? Well, I could rewrite that using Bayes' theorem. And then I can kind of get at some of these probabilities. So the underlying historical data to see kind of the underlying probability of people committing crimes to get some rough estimate of the probability of being innocent versus guilty. So these conditional probabilities in recent years, we can actually get a pretty good idea what those are. So given that someone's innocent, what's the probability that the jury actually found them guilty? Well, because of things like DNA evidence, and then they can go back in time and look at cases where somebody who was innocent was actually found guilty, but we now know they are innocent, right? Because of DNA evidence, they kind of retroactively went back and figured out, oh yeah, the jury got this wrong. So you can go back to all those old cases, figure out how many of them were overturned with DNA evidence, and you actually get a pretty good estimate of what that conditional probability is. You can then also do the same thing working in the other direction, which is figure out, you know, given that the jury found someone guilty, what's the probability that they actually were guilty, right? By looking at the overturned cases where the jury found them innocent and they were actually guilty, right? Same idea, condition on the same state of nature, 2 outcomes of the test, you can back that out. So people have done this now, and I think I had these timed wrong, but right, given that someone's guilty, the probability the jury finds them innocent, and given that someone's innocent, the jury finds them guilty, right? But this is an actual practical application of using Bayes' theorem, right? And we can really only do this now because you can go back and look at overturned cases, and so you know the actual underlying state of nature. You know, it's difficult to really know how many innocent people are in jail if you can't actually do that in terms of just figuring out what the probability is. Yeah.
This is random, but can you overturn, like, an overturn? Like, if you found someone guilty and then you find them innocent, and then,
I assume you can, but I would imagine not with DNA evidence. Unless it was like faulty lab work. But then you could just exclude that from when you're calculating your conditional probability. You would just exclude that case and say, yeah. So you would just reverse it to knowing that they actually were guilty. But I can't imagine like that DNA evidence would reverse a conviction and then reverse it the other way, unless the first reversal was because of some shady business in the lab or something along those lines. Yeah. I'm also not a lawyer. Ask Professor Nesson, or not Eric, but his wife. She would know much better than I would about that. All right. Any questions before we keep moving here? So I'll go through this I'll skip over these and we'll do these at the end of class. We talk about them. But I want to introduce the idea of these kind of discrete random variables that we'll be talking about the rest of the week. I'm going to go through this quick because it's kind of review initially of things that we've already done. So the first thing is we're looking at some variable, we'll call it a random variable. If we don't know the outcome, right, of some experiment. So this is going to look like what we've been talking about, right? We got some experiment. We don't know what the outcome is going to be. There's probably several different outcomes, but we could have it so that that random variable could take on any value or be continuous, or it could only take on a limited number or integer values, discrete, right? So we'll kind of write this random variable as just capital X. That's how we'll kind of, whatever the event, or, you know, whatever we're interested in, whatever experiment we're interested in, we'll kind of use the notation of capital X. Okay? Now, every single time we run this experiment, we're going to see different possible, like there's different possible outcomes we could see. So we're just going to call those small x subscript 1, small x subscript 2. This is the first outcome I could see. This is the second possible outcome, third. For a continuous variable, the problem would be that there would actually be an infinite number of these outcomes. If it's truly continuous, right, we could see any decimal. So that presents some challenges. We're not talking about continuous variables today or the rest of this week. So I'll kind of punt on that for right now. So for us with discrete random variables, there's going to be some limited number of possible outcomes we can see. So, you know, I'll go through this quick because I'm just reusing a slide that I showed you when we were talking about just general variables, not just random variables. Discrete, you can see the integers, but nothing in between. And then kind of that continuous variable, we can see any decimal, right? So that's just kind of a refresher of what that means. And now it's just that it's a random variable. We don't know what the outcome is, but we know it could be even these decimals are continuous, but only integer values if it's discrete. Okay. So that's kind of review. We're just kind of flying through that. So you can think about, you know, maybe I want to know the number of dependents on tax return or what family size is, well, there I should hopefully only see integers. Right? I shouldn't have half of a person reported as being part of the family. So, you know, they are random variable X. We select a family at random. We know we could see that they have 0 dependents, 1, 2, 3, 4, up to, I'm guessing roughly 20. I don't know what the largest family is, but around there. I can think about something like distance. Well, that's how far away from, you know, how far away from the store is my home. All the distance can be measured out to whatever decimal we want. So that's a continuous random variable. And then we'll kind of turn qualitative variables into discrete random variables. Okay. So I think I kind of mentioned this back when we were talking about qualitative and discrete, just regular variables, that let's say, oh, so the one where it's like, rate this professor, or do you agree, strongly agree, disagree, neutral? You could basically just code those as 1 through 5. In fact, I have to do that to then report what my average number is. And so there, the response was qualitative. If I ask somebody they own, what kind of pets they own, well, it's either no pet, dog only, cat only, or both, right? Well, I can just kind of identify those different responses with a number, right? So in the instance of like strongly agree to strongly disagree, I would just arrange those 1, 2, 3, 4, and 5. All right. Now, it's probably more useful when I have an ordinal variable to do that. You know, what's the average of kind of having a dog or cat ownership here? The mean and stuff wouldn't tell us as much. But when it comes to thinking about discrete random variables, right? If I code these as numbers, it's going to allow me to potentially come up with some measure of that central tendency. Now 2.5 is going to tell me that, you know, somewhere in between most people owning a dog or only a cat. It's a little bit harder to kind of interpret that. But we will start to do this where we kind of create these discrete random variables from outcomes that are actually qualitative, right? We'll just assign them a number instead. Right? So what we're going to be doing is then thinking about, we have all these possible outcomes. Right? So I can then show some type of distribution of what those outcomes are. So remember when we were doing frequency distributions, we were kind of giving this, you know, every different response, we were graphing the different frequency, but we then converted that into something else, which was relative frequencies. I could also graph out the distribution using relative frequencies, but relative frequencies, I was calculating how? Just taking the frequency and dividing it by total number of observations. So what I was really doing was just like we did with that contingency table Excel example last week, I was just creating probabilities. So I've got these different probabilities of all these different possible outcomes. I could just use those probabilities as my Y value, and the X kind of coordinates would just be kind of whatever these different outcome responses I could see are, and I can get a kind of this nice probability distribution. Now, we'll eventually talk about very specific probability mass functions. So this is going to be the idea that if I want to know the probability of seeing a certain value, there should be some function that tells me that. Now, this could be as simple as, well, here's a really simple example. Say I flip a coin, I don't know the outcome, but I know the probability that this random variable X shows up as a recorded response of heads would be 1/2. And I know the probability that it comes up tails is 1/2. This would be maybe the most simplest probability mass function. It is simply telling me the probability of all the different outcomes. So I only have 2 outcomes here, so it's not very interesting. And there's no functional form, like it's not following an actual function. But Wednesday and Friday, we'll actually talk about some examples like the binomial and the Poisson, where the probability of different outcomes, different values that X could take on, actually follows a functional form. So this probability mass function, if it's telling me the probability of seeing these different outcomes, what does it have to be between? The lowest possible probability is that it doesn't happen, or a probability of 0. The most uninteresting example is if something's guaranteed to happen, which would be a probability of 1. Just like relative frequencies. We said they had to be somewhere between 0 and 1. If I then take every possible, I know it's somewhere between 0 and 1. If I then take every possible outcome I could see for this random variable X, so let's say, I go back to this example, and I had some probability probability mass function that told me the probability of these different responses, right? Maybe this was 0.2, maybe this is 0.1, this is 0.5, and this is 0.2. Well, you either don't own a pet, you own both cats and dogs, or you own just one of each. So those probabilities should add up to 1, right? So if you take every possible outcome, right? So you go from the first to the very last possible outcome. You then take the probability that this random variable takes on that very first or lowest value all the way to the highest value. You then add up all those probabilities. Well, you've just taken the probability of every single possible outcome, added them up. You should have that entire experimental outcome space of 1. So when we were talking about these Venn diagrams and things like that, you really could still create visuals if you wanted to. Now, they're not going to be as clean or maybe as helpful, but you are really thinking about, like, all these different possible outcomes in this experimental outcome space. If I took the probability of every possible outcome, it should add up to 1. And the reason why is if we're doing with a discrete random variable, let's think about the family size one. If I select the family at random, if I think about the different outcomes I could see, they could have 0 children, 1 child, 2 children, 3, but they can't have exactly 3 children and exactly 5 children at the same time, right? Now, there's a cumulative idea that, if I've got 5, then I have at least 3, but to have just 3, that X is equal to only having 3 kids, I can't have only 3 kids or only 5 kids. So when we're dealing with these discrete random variables, essentially every single possible outcome, if I was to kind of give you a visual of this, every outcome should be what we call them. They can't see exactly 3 and exactly 5 at the same time. They're mutually exclusive. Every possible outcome is mutually exclusive. So it would almost be like, here's the probability of seeing 0 kids. Here's maybe the probability of seeing 1 kid. Here's the probability of seeing 2, 3, 4. I don't know. I don't know exactly what the relative size of these groups look like, but the idea is that every outcome would have kind of its own space within the entire experimental outcome space. And then when I add them all up, they should all add up to 1. Okay. So this is kind of like a bunch of things we've already kind of talked about, just in a slightly different context. Cumulative mass function, same idea. We go back to, how do I remember this? Cumulative GPAs, right? What's my GPA from currently all the way back to the beginning of time? What's the probability we see this random variable X take on this specific value for X or anything less than that? So this would be something like, what's the probability that I see someone have less than or equal to 3 kids, right? So this will become a little bit more interesting once we get to having symmetrical functional forms with a binomial and Poisson distribution. But for now, just think about it as cumulative, right? What's the probability I see a specific value or anything below that? So how could I find that? Well, if I wanted the probability visually of having 3 kids or less, all I would do is take the probability of having 3 kids, add to that the probability of having 2, add to that the probability of 1, add to that the probability of having 0, and then that should give me the probability of having 3 or less. Right? And the reason I can do that is because if I'm finding the union of 2 events, we said if they're mutually exclusive, that simplifies it down to that I only have to add up the probability of each event. There is no intersection that I double counted. Okay? So the highest, as we get to higher and higher X values, this cumulative mass function will get close to 1, right? If I tell you what's the probability to choose a household at random, they have less than 100 kids. Well, it's a guarantee, right? And if I say, what's the probability that, they have, I don't know, 0 kid, that's the small, that probability is getting closer to 0, right? There's probably better examples there than the kid example where you would see something that's like really close to 0 as you get this smaller and smaller like that. So, here, I'll kind of just go through this quickly. So this isn't maybe terrible. So if I had like a company, I had the number of new hires they had, and here's like some years they had 0 new hires. They never had more than 10. Most they ever had was 9. But I know that, they do have 12 positions. So it's technically possible that they could have complete turnover. Not very likely. In fact, based off the historical data, empirically, I assign probabilities of 0 here probably because it never happened. But I know they're possible outcomes. Right? I could have all 12 positions get turned over. So if I had something like this, it turns into a probability mass function. Right? I said sometimes it'll be as simple as telling you the different probabilities of these outcomes. Right? It's not going to follow a nice function. So all I would do is just like I created relative frequencies, I just divide by the whole number of observations I have. Once I divide by the total number of observations, I now have the probability that this random variable x takes on this specific x value. So probably they have 0 hires based off of historical data, 0. The probably have 1 higher, 0.06, so on and so forth. Okay. Like I said, this should just be a review, and then you can take those x values, you can take the probabilities as your y values, get a nice kind of visual, right? Just looks very similar to what we're doing with histograms, right? Same, it's really the same thing, right? It's just more generally, we usually are now thinking about this as trying to use this data then predict what the outcome of this random variable is going to be in the future, right? So based off the number of hires I saw this company have over the past, 35 years, I'm trying to predict, well, what's the number of expected hires I can see in the following. So it's going to look very similar to things we've already done, maybe weighted means, weighted variances, but it actually becomes a little bit easier. So we'll finish up talking about that, go over an example or two of those pretty quickly at the beginning of Wednesday's class, and then jump into binomials. Binomial distribution, that's that very last couple questions on the Excel assignment. So the bulk of the Excel you can get through. Those last few questions, we should cover how to do that on Wednesday. Okay? All right. I will see you guys on Wednesday.